With the ideal gas law that we talked about the last time, we now have a way to relate the pressure, volume, and temperature of a gas to the amount of a gas that's actually there. And ultimately, that's what chemists are often most interested in, is how much of that gas do I really have? So that's why the ideal gas law really helps us to get a handle on how much of a particular component is present. So that means if I know how many moles are present, I can do what? Stoichiometry, you got it. And stoichiometry can be done with reactions with gases, one of two different ways. One is that you're going to use the ideal gas law if you have a very specific condition where you are only relating gases. Then the mole ratios that you see in a balanced equation are going to be equivalent to the volume ratios, assuming that your pressure and temperature are constant. Okay, let me show you why that's the case. Here's the ideal gas law, PV equals nRT. So if I take the number of moles and I move it to the other side, so that I would have V over N, and then I take the pressure and I move it to this side, so I would have RT over P. What that tells me is that if we already know that R is constant, we know that T is constant and P is constant if that's going to be true for this particular equation. And so this whole thing just becomes one big unchanging number. If that's true, then the volume and mole ratios are actually also going to be an unchanging number. And so what's really nifty about that is that I can use the stoichiometric coefficients in an equation to do the stoichiometry with and not actually have to do all of the conversion back to moles, because I can go straight to number of liters. So if I have this equation, 3H2 plus N2 yields 2NH3. So I'm combining hydrogen gas and nitrogen gas to make ammonia. You are already aware that it will take 3 moles of hydrogen gas plus 1 mole of nitrogen gas to make 2 moles of ammonia. If, however, the pressure and the temperature are going to remain constant, then I can also say 3 liters of hydrogen gas will react with 1 liter of nitrogen gas to make 2 liters of ammonia. So let's say that I had 6 liters of hydrogen gas, and I want to know how much ammonia I'm going to end up with. Well, again, assuming pressure and temperature are constant, then I can take this and put it over 1, and I can just use the stoichiometric coefficients that are already in the equation. So from the equation, 3 liters of hydrogen is going to react to produce 2 liters of NH3. Again, the 2 and the 3 come directly from the equation, so liters of hydrogen cancels out, and that will give me 4 liters of NH3 that are going to be produced. Okay? Now, this only works, and I have to emphasize this, this only works if you're relating a gas to a gas. If you have a solid or a liquid or an aqueous solution, you can't do this. You can only do it if you're only relating gases. Now, there can be solids or aqueous solutions or liquids in the equation, but as long as you're only looking, like if you're given as a gas and what you're being asked for is a gas, then you can use this relationship. But if you need to use any other relationship, you're going to have to go back and do stoichiometry the other way. So we'll do a couple of examples of problems like that so you can see what that would look like. Okay, so once again, I've given you a couple of sample problems. So if you look at the first one, one way that hydrogen gas can be produced commercially is to react a strong acid with a metal. And so I've given you the equation there that 2HCl plus Zn yields hydrogen gas and zinc chloride. So I've got 512 grams of HCl being reacted with excess zinc at a temperature of 24 degrees Celsius and 0.95 atmospheres. I want to know what volume of hydrogen gas is going to be produced. Okay, now if you're looking at that equation, you look at the HCl and you look at the phase symbol after it, and it says aqueous after that. So what that means is that I can't use that nice simple relationship that we used in the problem that I just did, because HCl is not in a gaseous form. It is in a liquid form. It's been dissolved in water. It's aqueous, okay? So the first thing I have to do, just like I have to do with so many other stoichiometry problems, is I've got to take that mass in grams and I have to convert it to moles. So I'm going to start with 512 grams of HCl, put it over 1, convert it to moles as I've done so many times before. In 1 mole of HCl, use your periodic table. You see that hydrogen is 1.01, chlorine is 35.45, so if I add that together, I get 36.46 grams of HCl. So grams of HCl will cancel out. Now I'm trying to find the amount of hydrogen gas that's going to be produced. And so now I'm going to use the coefficients in the balanced equation. And so if you look at the balanced equation that's there, there are 2 moles of HCl in that equation for every 1 mole of H2 that's going to be produced. So moles of HCl will cancel, giving me moles of hydrogen gas, and I will end up with 7.02 moles of hydrogen gas. Okay, so that's moles. The question says what volume of hydrogen gas is going to be produced. Well, if I'm going to convert moles into liters, I'm going to have to use the ideal gas law. PV equals nRT. Remember that I have to watch units on this so that it matches up with my ideal gas constant. So it tells me that I have 0.95 atmospheres, which works with the ideal gas constant. Volume is what I'm trying to find. I already know that I have 7.02 moles. Ideal gas constant, 0.0821 liter atmosphere over mole Kelvin. It tells me that I'm at 24 degrees Celsius. Remember, you cannot use Celsius, you have to use Kelvin in all gas laws. So I'm going to take that 24 degrees Celsius and I'm going to add it to 273 to end up with my Kelvin temperature. And you're going to end up with a Kelvin temperature of 297 when you do that. So the 297 Kelvin is what will go here. Multiply these 3 numbers together, divide by the number of atmospheres, and you will end up with 180 liters of hydrogen gas. Okay, just 2 significant figures because that's all that my pressure was given in. Okay, so kind of an overview here. I started out with grams, so I went from grams to moles. Okay, that part should look real familiar. Only difference here is that I now have to take moles and then use the ideal gas law and convert it to volume. Okay, sometimes depending on what you've been given, you're going to start with the ideal gas law in place of end with the ideal gas law. So on the next page there, we've got another problem. So we will make some more space for that second problem. And the problem says to make magnesium hydroxide, a major component in some stomach antacids, hot water vapor is passed over solid magnesium. So I've got 4.5 liters of water vapor at 200 degrees Celsius and 4.94 atmospheres, and it's passed over excess magnesium. How many grams of magnesium hydroxide will be produced? Well, again, I've started with a gas, but what I'm looking for isn't a gas. What I'm looking for is the solid that's going to be produced. So I'm going to have to use a combination of my regular stoichiometry procedures as well as the ideal gas law. I have 4.5 liters of water vapor, so I've got to take that first and convert it into moles. So in order to do that, I have to use the ideal gas law. So PV equals nRT. The pressure that they gave me, 4.94 atmospheres. They told me that I had 4.50 liters of water vapor. Number of moles is what I'm trying to find. That's my whole goal here. ideal gas law constant. And then the temperature I'm given says 200 degrees Celsius. In this case, I need to add 273.15 to that, and I'm going to end up with 473 Kelvin. Okay, because 273 plus 200 is 473. And then if I multiply these two together, divide by these two numbers, N is going to come out to be 0.572 moles. Okay, and that is moles of water vapor. So now that I have moles of water vapor, I can then take that and convert it to the amount of magnesium hydroxide that I will end up with. So this is just the regular stoichiometry part, 0.572 moles of water. Put that over 1. From the balanced equation, you see 2 moles of water on the left-hand side, and you see 1 mole of magnesium hydroxide on the right-hand side, so moles of water cancels out. The question asks how many grams of magnesium hydroxide, so I'm just going to go ahead and convert that to grams. In 1 mole of magnesium hydroxide, you use your periodic table. Magnesium's about 24, oxygen's about, whoops, I got that subscript in the wrong place, got in too big of a hurry there. Oxygen's about 16, hydrogen's about 1, so that's going to give you 58.33 grams of magnesium hydroxide per mole, so moles will cancel out. And then when you multiply all that through, you should end up with 16.7 grams of magnesium hydroxide. Okay, so again, to kind of summarize that for you, in this case, because the information we had was about the gas, we had to use the ideal gas law first and come up with number of moles. Then once we had moles of the given, we could go to moles of the asked for and then convert it to grams of the asked for. Okay, 3 significant figures in your final answer there. All right, so that's stoichiometry using gas laws, and so that's what you're going to be practicing today.